Okay, well, everyone, hey, let's dive in. I've got cover sort of a history of launching composites or attempting to get composite material structures into space. And when I refer to the word composites, I'm really referring to polymer matrix composites. And I'd like to show you and share with you, the sort of the evolution of, and then maybe if we have some time, I'll get into some challenges and some case studies. I don't think we'll have quite enough time. So my outline is I'll hit my personal background, a history of composites in space, unique challenges that we've faced, and some lessons learned along the way. And then I try to hit these a little fast. My background is, as Dan already outlined, I'm a mechanical engineer that started off in that arena, really focused on an interest in composite laminate theory, attempting to build composite structures. And I started there at North Dakota State University with a hybrid degree in polymer chemistry and did advanced study at Texas A&M University, specifically focused on composite materials. Next slide. So I've got just a little background. My personal career, Dan hit it. I've worked quite a while all at Johnson Space Center, and my real focus, and I'll show you some of the programs that I've worked on there on maybe the next slide.
Hey, Jeremy, you're dropping a little bit. Maybe take your video off to kind of help.
Yeah, let's do that. Thank you. I hope that works.
Perfect. Yeah, let's give it a try.
Apologies. This is a little clumsy because we're back and forth on the slides. My personal background, I kind of grew up looking at the stars, imagining about space, and it was really my pursuit and my dream to get away from farming, if you will, and get up into the arena that I'm in now, which is spaceflight. We animate down and we'll click to the next slide. Those are just some of my personal interests. I'd like to give you a little background about myself. I'm an outdoorsman. I enjoy sports and athletics, music. Homebrewing is my hobby. That's just a little personal tidbit. There we go. Okay, so let's jump in. Next. So it all began with, and when I think of space and our evolution of technology, it all began with aviation. And so this is just a clip, kind of showing how really all of human spaceflight in particular, even just general space, really is standing on the shoulders of all the technologies that began with aviation. Next slide. Here's a nice fun poster that for history, and it shows this evolution connection from early aviation all the way to the space shuttle. I kind of find it interesting how large they put the space shuttle as kind of the pinnacle of this journey. It's really not. There've been sort of parallel journeys since the time of the space shuttle program, but up until that point, it was very much standing on the shoulders of aviation. Next slide. And so just hit the down arrows as you wander through this. I wanted to show you the evolution of putting composite materials, polymer matrix composites, into aviation applications has been a fairly slow journey. And it started with the F-14 vertical tail. And if you keep pushing down, you'll see the pictures are kind of animating with time. 8% on the Y. The space shuttle orbiter here, was only about 10% by weight. And look at all the airplane applications below it are in the 1, 2, 3, 4, 5%. And so as we go along, you'll see as time evolves, we've gotten to the point now where we're up at the 787 and F-35, the A350, we're getting to around 50% of composites by weight. By volume, those applications are over 80% or so. But by weight, we're only about 50%. And the pinnacle here is the Starship that achieved around 70%, the Beechcraft Starship back in the 80s. And that had a horrendous history of problems that caused that program to retire that application. Probably the one that's the most aggressive out there. And it wasn't just because of lightweight that the B-2 bomber was after polymer matrix composites. It was more of its radar signature. And so if you think about the history of aviation, now we go look at space. Hit the down arrow. I'm going to leave you hanging just for a minute. And let's go talk about what's happened before I come and show you what this chart looks like for space. So next slide. So this journey of putting lightweight structures into space, our most challenging efforts really have been going to the moon from a mass standpoint. And if you talk to the old timers that worked the Apollo lander, um, the LEM, they'll tell you that they didn't have any polymer matrix composites. They didn't have polymer matrix composite structures on anything on Apollo, except for this one little application. Right, there was a phenolic fiberglass honeycomb core that was bonded to stainless steel sandwich structure, and that was filled with what we call today Avcoat from the National Air and Space Museum. And you can go see what that looks like today. But essentially, the Apollo era, that entire rocket had no polymer matrix composites anywhere on it. It was all metallic structures. So then we came to the era of this of in the late 60s or late middle 70s, early 80s, the space shuttle program began, and I'll show you where composites were employed. Next slide. I already showed you that the orbiter was about 10% by mass itself. Other parts of the vehicle were much, much less. On the solid rocket motor, we used a phenolic. You see on the bottom left the man standing inside, about the approximate size of that. That was on the solid rocket motors, and really that was the only composite component that was put onto the solid rocket motors. Next slide. I'm gonna try to go through these fairly quickly. On the large external tank, that massive tank, the only composite part was the nose cone. Next slide. Actually, there were some small fairings and access doors, but pretty insignificant. On the orbiter, we got probably around 10% or less. Somewhat. First off, inside the wings, there was a boron epoxy as stiffeners. On the aft part of the vehicle, you'll see there's this OMS pods where the engines are all packed, and I'll show you another picture of this. And the payload bay doors was a significant one. You see that here. And those were very large sandwich structures. We had a lot of lessons learned from this that we've employed and we've learned from today on what not to do. Application. Those there are the OMS pods, the orbiter maneuvering system, the shrouds or the outer shell. Next slide. Quite a bit of mass was saved on the robotic arm. This was done by the Canadians in partnership with the United States. And that entire robotic arm is a very, very thin-walled composite cylinder. Fairly simple structure, but it's very, very, very optimized. That structure cannot even lift its own mass here on Earth. It's been designed so efficiently that it can only basically. A significant amount of mass was saved in the first real pretty heavy implementation of composite over wrap pressure vessels. NASA has worked relentlessly in this area because we operate at pressures that are much, much higher than what airplanes use or civil transport use because we have to. We can't afford to. So we pressurize these at like 5,000 or 6,000 psi. Program utilized Kevlar as its filament winding material of choice, and we saved a significant amount of mass doing that. Today, we've moved to carbon fiber. Next chart. This is kind of a fun one. Early on, the early spacesuits were all bladders, and if you've seen around the moon, you notice it was basically being inside of a balloon. And in the 70s, NASA and early 80s worked on the evolution of a new spacesuit. We're doing another suit today. But what we learned was you need some hard structures inside. And this was built out of just fiberglass, very, very damage tolerance. And in the shoulder rings and rotational joints that can be bearings that can rotate. Next slide.
Hey, Jeremy.
Yes.
Your sound's cutting out a little bit. I think we can manage. I just didn't know if it's cutting out because of proximity or bandwidth. So if you're moving around, you're solid when and then it kind of cuts out. But we'll keep going.
Yeah, interrupt me again if I need to move. I'm gonna move location.
Okay, sounds good. Yep.
Hey, great, thank you, Dan. Hey, so the space station, right? This thing must be packed full of composites. You think that this huge assembly, when you look at it, all of these structures holding it all together, and it turns out that there wasn't much deployed in the regime of composite polymer matrix composite materials. And the reason it is that the space shuttle orbiter had such an capacity that it wasn't necessary to save mass. And so really we just kind of dumbed things down and pushed up a bunch of aluminum structures. Next slide. There were composites applied in some areas. This one is the solar array wings, and you can see this is an expanding, kind of like a big truss with springs. And in this instance, we had some, they were aluminum, basically springs that compressed, as you can see. I won't get into this too much. Next slide. Again, the robotic arm, built by the Canadians, was optimized out of carbon composites, and damage tolerance, turns out, has been a big um, challenge for this. We've had micrometeor board and orbital debris that have damaged the robotic arms on the space station early, because the damage tolerance testing, it turns out, was necessary. All over on the inside of the space station, our composites were used. You can see simply the black components there were the face sheets. Most of those structures, again, were aluminum, and the only opportunity there was basically the skins of the ISS stowage racks. Next slide. I got to work on the crew quarters. This is, we did get a bit more mass out of this structure. It is carried to orbit later in the program, and you can see the composites utilized there as sandwich assembly. Next slide. The nitrogen oxygen resupply tanks. This was a big challenge in more recent times, trying to resupply consumables to the space station. So we send up both nitrogen and oxygen. These tanks are fairly large, and we pressurize them and ship them around the world to launch resupply. And then this is kind of a fun one. If you hit the down arrow a couple, I think 2 more times, you'll see some more pictures kind of pop in. This is called IROSA, and there's a picture of an astronaut there next to this mandrel, and you'll see on the left and right, close to you, there's a flattened composite tube that effectively, so this would be like taking a straw up, and then its sort of viscoelastic behavior wants to return it back to its original shape. It becomes a spring. And what we've done today, if you hit one more slide or one more down arrow, I think there you'll see what we're doing today is we're replacing the space station solar arrays, and you can see the size difference. We're actually increasing the power output with a smaller solar array, and that's just simply due to the increased efficiencies in either side. You can't quite see it in the picture. Are those two serve two functions. It serves both as the structural component that holds the solar arrays out and in place and keeps them from interfering or contacting the rest of the structures behind as the mechanism. The X-38 crew return vehicle, built in the late 1990s, 2000s, I got to work on this. We built all of the outer with cyanide ester composite solid laminates. It was a very dear learning experience for me, because that was my first opportunity to really fully own the composite development of a spacecraft like this. And this work eventually worked its way into the program that we now are aware of as Dream Chaser, that Dan Polis has led. Next slide. James Webb Space Telescope, I just had this as a shout out. It's pretty neat. I think, Dan, you worked on this.
Yep, spent a good number of years on it.
It's really, really proud of this work. And yeah, if you can see that composite truss there, it's an incredible piece of work that's adhesively bonded composite structures, very minimal use of fasteners, very optimized, and it folds itself up. It's It's pretty amazing. And in this instance, composites are selected, I believe, Dan, primarily for, matte E, right?
All for thermal distortion reasons.
There you go. Yeah, so they have their very unique capability to design a minimal or sort of zero CTE thermal expansion at the larger structure level, which you basically just cannot do that with metals. Next slide. Okay, so Orion, we'll hit the next one. Orion was our first big step forward in an integrated. You now are aware of the Commercial Crew Program that's heavy in play. But when Orion came along, times had changed. There's been a big gap, late 70s all the way to the early 2000s when the Orion program started. And if you hit the next slide, you'll see that we put quite a bit of composites into this vehicle. This was really my baby, as I would say. It's something that I personally, and I've managed the development, the composite building block, the characterization, all the M&P that kind of is associated with this effort. And this is an exploded view of the Orion, and what you're looking at is almost everything you see are composites. What I don't have immediately shown is the pressure vessel inside of the command module, the crew module there, is an aluminum assembly that's welded significant amount of the mass. There are some frames and some, I think some longerons in the service module. This is built by the Europeans. They didn't get quite as aggressive in the composite area as the rest of this program did. And this effort achieved approximately just north of 50% by mass. It's about 75% by volume in composite structures. Next. Yeah, let's just buzz through this. Keep it in the down arrow. I just threw in some pictures so you guys could see, some of those composite applications and some of their design features. Next. Here's the outer mold line or the thermal protection carrier structure. TPS makes a very nice application because we can use higher temperature materials. Specifically, we've used cyanide ester materials for. Instead of using a sandwich assembly with basically a skin structure, all a titanium structure. And this specifically came out of the Mars lander program, where we'd worked with Lockheed Martin and have this kind of heritage history in using this sort of an architecture for a heat shield design, and that's what we've maintained on the Orion. Next slide. Okay, so SLS. Now we're back to rockets, and we got this big monster rocket, right? And if you hit the next slide, you'll find that there's not a lot of composite structures on here again, and it's a bit of a surprise to me. Not that I'm for composites to win against metals, but I think they have a place. And in some instances, like a cryogenic pressure tank, it turns out that composites are really hard and they come with a lot of risks. So using aluminum for huge cryogenic storage tanks, it makes a lot of sense. But in this instance, you'll see the little adapter and the upper stage adapter, about the only two parts on that vehicle that are composites. A more notable application of composites is in fact in the solid rocket booster. So we're going to a 5-segment booster instead of 4 like it was on the space shuttle. If you hit the down arrow, you'll get a picture. This SLS, unfortunately, the trajectory is forcing to throw away the solid rocket motors, or to catch them way out in the deep Atlantic. It's so far out based upon the trajectory that it would be very difficult to recover, like we did in the space shuttle program. So they're going to dispose of them, and we're using the ones from the space shuttle, which were made out of D6AC steel. But here's an example of a very large composite motor segment that is being manufactured by ATK Corporation, renowned Northrop Grumman in Utah. And that component will be all composites. I'm about done with it. Is an evolving area where we are seeing the application of lightweight composite structures just growing enormously. It's an exponential growth curve here. And these are just a number of examples in the commercial space sector that are pushing designs to be lighter and more efficient. Next slide. And then as I look forward to the future, we've got some pretty, hey, Dan, am I coming through better? Did it improve? The
You know,
audio?
about the same, Jeremy, but it's manageable. So I think just yeah, no adjustments necessary.
Okay.
Like, yeah, brief cutout.
Great. Okay. So yeah, so our future looking forward is more aggressive. And I told you earlier that landers have been some of our biggest challenge areas. You know, that may be an area where we really see some push to improve in that arena. And one of the biggest places to improve on is this, which is all composite cryo tanks. I've had some colleagues that worked at Virgin Space that were pretty heavily engaged, and that company is now falling apart, unfortunately. But the current players are really Boeing and Firefly. You arrow down, you'll see Firefly on the right. In 2014, NASA did a pretty big investment and partnered with Boeing to build a very large tank, a 5.5 meter diameter cryogenic tank for liquid oxygen, liquid hydrogen. And it was very successful. It passed all its leak tests and its leak rates. It did structural integrated testing. And then more recently in 2022, Boeing continued that work with the DARPA program and built a composite cryotank that very nicely could fit into this stage. This is the rocket engine system that would push our. And so there's a trade going on at the moment to see if we could get that sort of lightweight system. That would by itself improve our payload capability to the moon by 30%. So it's very, very big. It's a big deal. Firefly on the right is successfully now launching really the first ever bottom to the top, the structure, the tanks, pretty much everything on this thing, you know, aside from the rocket engines and the mechanisms, are composite structures, both tanks and dry structures. And then looking forward, this is the end of the history, I guess. We've got a lot more coming. There's Gateway and Orbital Reef that the agency is working on. And, you know, I don't just work on composites, but it's certainly a focus area of mine. And we're seeing more opportunities because in particular, as to the moon, it becomes even more important to save weight. Okay, so back to that chart. Where did we land? If you hit the down arrow, I've got it animated again, so you can kind of step through it. So the shuttle orbiter started at 10%. X-38 back in that time was around 20%. In the 2010 timeframe or so, we got into this is the early cargo program for space vehicle, achieved around 50% by weight. X-37B, I have kind of a shout out in there. It's not a human rated vehicle and it does not have a pressurized volume in it. But X-37 did achieve over 80% composites. It's pretty much bonded structure everywhere, secondary bonded. It's not perhaps what we would do for a human rated application, but it was very aggressive. In 2011, Dan Polis worked on that NASA composite crew module and they achieved north of 7 by weight. Orion around 50% in the 2014 timeframe. In the 2019 timeframe was its first flight at about 30%. And you'll notice that they're quite a bit down. But I will say that Boeing was very, very judicious and careful about their choices relative to cost and, you know, versus the necessity to save weight. And I think that they made some smart trades to moving a number of their components to metallics. That's just the basic, not the rocket, but just the pressure vessel itself was upwards of 60 to 70%. And then Spaceship Two in 2021 and Dream Chaser here coming up in 2024 are on the 80% of composite by weight, and that's enormous. It's almost, I don't know, Dan, what would you say by volume you guys are? By weight, you're about 80% on Dream Chaser. I think you've achieved the holy grail in my
Yeah, I don't know.
95%.
Yeah. Yep.
Okay. All right. So unique challenges. Let's step in and let's talk. I'd like to talk about some of the hardships that we have in doing what we just kind of showed you. And I won't have time to go through all of this, but first off, the premise is, you know, I told you earlier that our technologies are really stood on the shoulders of airplanes. Yet, in fact, definitely not airplanes. And if you hit the down arrow, I think there's a
Hey,
few.
Jeremy. Hey,
Yes.
Jeremy. We lost you there, and I thought that was probably an important point to maybe
Oh,
just rehash.
oh, sorry. Okay. I'm trying to figure out why I've got a hiccup with my internet. Apologies, everyone. Saying that our spacecraft really aviation. Yet, when we think about what it is we need to certify, survive, and to endure in our mission, as well as if we think about what environments we have as threats that are on the ground, spacecraft are absolutely not aircraft. And so we have to find a way to depart in how we do things in terms of how we're very low volume typically. And aircraft are produced on an assembly line. Aviation sector cannot afford to find out mistakes or to learn something late in their production. It would be catastrophic to the company. Whereas we have the we go, or maybe even fly a few times. We might consider certification being the point in which you're happy, but iterate our certification strategies basically as a function of actually flying our vehicles. Oftentimes, our production flights are just like test flights for airplanes. Design drivers, static strength are commonly the driver. We don't know much about fatigue like you do in airplanes. The damage threats is one of the biggest ones. And in space, you know, we've got space junk flying around. Speaking, our biggest threats tend to be humans and their interaction with the spacecraft that we operate around. And in our instance, we don't have to think about luggage banging into the side of a spacecraft like you do an airplane, and that is a drastic difference in damage. Hit the arrow two more times, I think. Environments are obviously different, and then our load paths. This is a big one. Airplanes, and I'm quite thankful of this every time I get on the right. You know, every wing spar in that wing, you could come out there and take a chainsaw and you could cut through that wing spar. And that vehicle's been designed to safely redistribute its load to the rest of the remaining structure. The pressure vessel can be said the same. Most all of that structure operates that way. And so it's very fail safe. And that comes at a significant increase in mass, which unfortunately we do not have redundant load paths in our structures. And then last, proof testing and inspection as a part of our operational strategy absolutely can be a big part of working a spacecraft program. Aircraft, which that wouldn't work. You couldn't stop and get an NDE inspection every time you fly. Otherwise, you'd have no revenue flying airplanes. For me, thank you. So I'm going to just list real quickly. We'll flip past this slide pretty fast. But these are just some of the listed differences that we've got to consider. Flammability turns out is a very big one for us as we think about going to the moon because we want to push our oxygen levels upwards. The spacesuit operates at only about 3 psi of 100% oxygen. And it's critical that we have a pre-breathe environment that we can go be upwards of around 37% of oxygen. Unfortunately, most all epoxy systems, polymer matrix epoxies, will readily burn in that kind of environment. So it's a pretty big evolving challenge for us. Thermal cycling is a big one. Matrix cracking, when you get really cold, especially in those cryogenic applications, they tend to micro crack. That's a problem not only for cryogenic storage, it's a problem for habitats. Because if you get matrix cracking, gas, you know, you keep sending tanks to the moon trying to replenish the gas. We don't have enough tanks coming. And then space environmental degradation is another one associated with proton radiation, galactic cosmic radiation. And then last, electromagnetic interference is also a unique challenge in space because we don't have an atmosphere around us to ground the spacecraft to. Next chart. And so this is, everybody sort of knows why, but I just want to highlight composite materials. People think of strength, but if you look on the right, this is the specific tensile strength on the vertical axis, and then it's got both that and the specific strength. Specific strength is in red, and I'm sorry, strength is in red, and stiffness is in flip-flop, sorry, blue, and then stiffness is in red. And for 100 KSI common quasi-isotropic polymer matrix composite laminate, we've basically out of the water when it comes to strength and stiffness. But when you think of strength, we can't design to this kind of optimal are still brittle materials. And so when we start to damage the structures, we put defects in that could really be in the structure from impacts or otherwise. We have to knock that number down significantly by at least half. And you can see it, then it doesn't become as competitive as it looks like on this chart. However, like bending stiffness, you still have that benefit, even with damage. And so what happens is we think of stiffness commonly drives a lot of our spacecraft structures. So that puts us to sandwich, which is on this chart. And so if you can animate through this, oh, sorry, I hit the down arrow, not sandwich, bad joke. Composite laminate sandwich. So when we put aluminum honeycomb core in, my bending stiffness goes up substantially. And for many applications, you have a massive benefit of increased bending stiffness. So this bottom chart on the right shows you just a quick look at a solid material at a given density and or a given stiffness. And you compare that to simply increasing that to a core density, say about twice the thickness, you increase stiffness by 7 times, and by 3 times core thickness, or very close. You can see the weight on the bottom goes from 1.0 to 1.03 to 1.06. So with about a 6% increase in mass, you can increase the bending or flexural stiffness by a factor of 37 times. This is the real reason why many of our composite structures win for space applications, especially when you consider buckling instability as a driving force when you launch a... Next slide. So I told you earlier that we can't utilize that specific strength value that's up at the top of that comparison chart compared to aluminum or other materials, because we have to think about damage tolerance. And I consider this still to be our most challenging area in deploying composite structures into spacecraft. If you talk to the folks in aviation, they'll tell you the same. This is still at getting mass out of their structures. So if many of them are, we do have more tolerance to damage than we do if it's designed by strength. So a common approach for us to account for this kind of effective defects or damage, since polymer matrix composites are fairly brittle and they can fail, they can have substantial reductions in strength fairly quickly with impact damage. A common practice is to design to an open hole for impact coupon strength property. And you can expect that will be a reduction 50%, typically 50 to 60% a reduction from its pristine state. That's a huge knockdown. And in many cases, it's imperative that we do so. And in some cases, it turns out that knockdown isn't even enough, depending upon the architecture you pick for your material system. And so CM817 of a building block. And many of us that have worked, through developing a composite structures from the ground at the bottom of these coupons to elements to full scale, all the way up to these vehicle level tests, will tell you that sometimes we learn our greatest lessons right here in the middle when we're testing a full scale element or design feature. And so say is that as we're doing this work, we need to characterize this idea of putting damage into our test campaign at the building block level at all levels. And damage needs to represent not only, say, impact damage threats, but also manufacturing variability, voids and porosity, delaminations, foreign object debris, that sort of thing. And I will say that we have become, as it's listed, we do a sort of a hybrid approach. I'll talk more about that. Failure modes, I don't need to get into all of these. I just want to say that generally speaking, in that chart, one of the problems is since there are so many failure modes associated with sandwich, it's common that we learn about a funky, unexpected, or unusual failure mode on a structural design feature very late. We can find that we've wasted a lot of time. So understanding this is critical. Next slide. And I think this is just showing some more geometry of failure modes. We don't have to go over this other than to say that if you imagine at the bottom of that building block, if you spent all of your time up front just doing a bunch of coupon testing at the pristine level, and then you think you got everything smart and you get into your program, now before you start to learn how this stuff really works, you're going to be in trouble. Next slide. Let's skip this chart. If you can hit the down arrow. Just going to point out that if you test quasi-isotropic laminates, or I'm sorry, if you use composite laminate, the one point, composite laminate theory is really helpful theoretically, right? But when it comes down to the actual verification, if we have to count for damage tolerance, especially at the end of the day, shouldn't be what drives our test campaign, composite laminate theory. And in fact, we need to get into real testing of real structures. This is just a word on lamina versus laminate testing. I learned this from the F-22 and F-35 program when I was interested in I learned from some of their testing. When you isolate, even if you use cross-ply laminates or lamina level testing, like a 090 lamina, for those that are familiar with ASTM standard testing for composites, and you're trying to get lamina properties, if you just do lamina tests, you'll find that your statistical properties will end up being lower than they do if, in fact, and then you use reverse composite. It's a little bit complicated, but you'll actually improve your strength values. This would really be for pristine strength, or for, say, things like modulus or stiffness. And so, anyway, yeah. So, big thing on damage tolerance. And I honestly believe that structures, not just those that are human rating, a careful strategy to interrogate effective defects and damage that can really be in the structure. We call it, say, worst case credible, or NASA now uses a term called the residual threat determination, the RTD. And the idea is that you think through very carefully what are all the sources of defects from any source through time. And you tend to try to design a test campaign that interrogates the effective defects. And in that way, this idea of pristine properties becomes almost irrelevant. It's only really necessary for stiffness-driven calculations like modulus, Poisson's ratio. But strength, we need to get into damage tolerance. And so if you think about a composite strength, tension, say at 100%, compression, pristine is like half of that. Open hole compression, the one I threw out earlier as a starting point, is another half of that. And so this is the really limiting factor. If you have a tension-based design, composites are a smoking winner. But if it's compression-driven, you can see that I can't really capitalize on all the capability that composites afford me. Next slide. And then you can just bounce through this. I had this animated too. So I just wanted to make a point here. This is what, wow, this is pretty extreme, isn't it? But the aviation threat environment as you can see, is vastly different. Think about a military airplane. They're not just designing for like a baggage cart running into it. They're designing for bullets and shells and flak and everything else you can imagine, right? And hit the down arrow. That this is not at all what we got to think about. Think about damage tolerance. We're thinking about damage. I'm thinking about an astronaut getting in and out of a suit and banging their head on the side of it, or setting it down in a rough way and banging it around a little bit, right? But even then, knowing it's a spacesuit, they're going to be gentle with it. Um, in space, we actually lost one of the ammonia loops on the space station because we had space junk come fly through one of the radiator panels, and it caused a delamination of a composite sandwich, caused a thermal problem. We had to isolate that particular ammonia line on this on station. Sorry. Here ones is just when we're manufacturing hardware. This is a picture of one of the components on Orion where we had a tooling path that was misprogrammed, and we had the robots smash into the side of a $1 million part. So these are the real. Next slide. Okay, so when we get into testing, and I'm telling you, we got to test for damage tolerance. Now I'll disclose that our test methods, they really kind of suck. And this ASTM standard way to do this from a compression after impact standpoint is to utilize this ASTM 7136. On the left is a picture of a drop tower. I want to make a quick point that you'll find people have been using drop towers that are really aircraft energies, which is 50, 60, 100 foot-pounds, and they use a fairly high mass. If you get into a study about impact damage and you're trying to actually characterize or size or interrogate the kind of threat that is real to you, for most of our spacecraft world threats, they're tool drops or somebody's elbow banging into a structure, right? On something in the wrong place. And in that instance, for a tool drop, 1/2 mv squared does not equal 1/2 mv squared when the mass and the velocity change. And we've done some work there to show that if you're dropping a tool and that's your real threat environment, and you should probably get that right. And in this instance, we've got a custom design impactor that allows us to drop basically the mass of a tool, 1 or 2 pounds. Vastly changes the kind of damage. Another quick point, edgewise compression is kind of an ASTM standard that everybody goes to that's associated with that drop tower standard. A fun fact, it is substantially better to utilize something like a long beam flex test that you see in the bottom middle. A 4-point beam bending test allows you to, say, impact one surface of a sandwich assembly and intentionally put only that surface into compression and keep the tension. And what that does is it eliminates all the complex buckling instability failure modes that can complicate the results. And in fact, it produces a much better statistical scatter that you can utilize for allowables development. Okay, next slide. So I wanted to show you some data to just to give you some analogs on this. And so if we think about like that test that I just showed you, right? And let's look at some actual test data of solid laminates. This is a quasi-isotropic carbon epoxy CAI test campaign that I ran here in Houston at Johnson Space Center. And you'll see 16, 24, 32, 48 plies that are kind of peppered into this test result. And if I look at these little lines on here, first off, my average pristine strength is up here at 100%. And if you hit one more arrow down, it'll show the regression curve fit. So if I'm doing open hole allowables, right? First off, if I was using the pristine strength, I would be, even on A basis allowable, right? I'm way up here, way too high. Because if I do any damage to this component, I'm gonna have trouble. And you can see it drops off, it falls off pretty quickly. Even at 5, 10 foot-pounds, I'm getting huge reductions in strength. And if I look at the open hole compression value that you might get from a material data sheet or testing yourself, that number being around 45% of its pristine. And if now I look at where does that cross over on my regression curve fit value, I'm I'm less than, say, 10 foot-pounds, and I'm in trouble. And so you can see the two circles there. Civil transport aviation, for airplanes that you fly in on a common basis, they're designed for the kind of damage you see there way over on the right. And the good news is they're on the flat of the damage tolerance strength curve. And that's a good thing, because if they miss the amount of energy that they might be designing to, plus or minus, hopefully that structure doesn't fall apart. Unfortunately, for spacecraft, we're way over here on the left, on the steep part of the curve, and this is where it gets difficult. Next slide.
Hey, Jeremy, I'm going to give you a 5-minute warning.
Perfect. I'm almost done with this. So here's an example of a spacecraft, really sporty aluminum honeycomb sandwich assembly that has been tested for that circle on the left. This would be like zooming in on that circle now. And when I have really thin face sheets, okay, very little damage that I can tolerate. And so if you look at that same 100% at the top where the green line is, and now if I look at where my regression curve fit on my test data actually crosses over my open hole allowable, you can see that the amount of damage energy that I can tolerate realistically with this 4-ply structure before I reduce the strengths below my design value is only less than half of a foot-pound. And so you can find out that pretty quickly that you got to really, really watch, be careful about thin sandwich assemblies, because in fact, very, very small, I mean, at half a foot-pound is enough in bumping your elbow on something, right? And you dent in there. And if you're not careful, you can tell yourself, hey, I'll compression allowable, and I'm going to be good, right? That's what everybody does. Well, it might work for what we just showed you on solid laminates where your 16 plies or greater, but it's not going to work for you on something very, very thin and optimized like a 4-ply face sheet sandwich structure. Next slide. Okay, let's skip over this. That fatigue, generally speaking, is not much of a concern for damage tolerance. We don't really have to think about fatigue that much. We've done very limited testing to validate that we don't have a concern. And then hit the down arrow a couple of times. There's a lot to look at here. I want to give you the takeaway. This is data on dent depth versus visible inspection or is that you can have for thicker laminates, you can have almost no dent depth, which is the plot on the top. Look at the X's, and you'll see at very high energy levels, maybe 100 foot-pounds or so, I've got dent depths of 50 thousandths. But yet if I look at the subsurface damage area at that 48 ply data point, I got 5 square inches of nations. So just the point is visible damage isn't very reliable for us. Structures. Okay, next slide. Okay, so this will be my last chart to kind of talk. So if I think about the design space, that curve I just showed you, residual strength versus, say, damage size, or we've got this idea that we want to design to sort of understand what that means relative to NDE, and the other is relative to what's the worst case credible defect that we could put into our structure. And we need to certify design that we can tolerate that kind of damage into our structure and write margins against that. And so our typical design ultimate load requirement of 1.4 times design limit load needs to be to the right of this. And from a worst case credible, what's the worst thing that could happen that we think that it component, we need to show that we can at least tolerate that to a safety factor of 1.0. But if every flight we were able to do something like an NDE inspection, we can push that space. That's okay. You can go to the next one because I'm illustrating it on the next one, and this will be the last slide. So I think, there we go. So if we think about our damage all the way to the yellow box, and the amount of impact energy they have, huge. Same thing with the barely visible damage. And I just showed you that you might have 100 foot-pounds of damage before you can see it. So you have to design to a huge, huge threat envelope. And what that means is composite airplanes today are so over-designed. If you talk to the folks at Boeing and Airbus, they'll tell you that they would fly on a composite airplane, metallic one, because they know how over-designed they are for this. And yet we can't do that in space. And so there's an idea that we can push down our design envelope to a much smaller green space for spacecraft because we can control the environments better about what our threats actually are. We can exercise something like a proof test campaign to screen out the kind of defect that could have worked its way into the structure all the way to the right. And we can use in the program to push down the top of the box relative to designing. This is a huge mass opportunity for us to save weight in space, and if we don't do this, we of composites that we can get into spacecraft. So that's about all I had. I had a summary chart at the very end, but we can pause, take questions,
Yeah.
chat a little bit.
Yeah, well, let's make sure we leave time for questions. So first, I see a few, but folks, put your questions in the Q&A box. So Jeremy, I thought that was great. You know, you and I have been talking this stuff for years, and you know, I was still super interested to see all of it and how it fits together with the history lesson was great. I will say, just for some people on the line, you know, that I think for unmanned, I mean, Goddard, you know, James Webb's a great example. You know, we design to pristine properties all the time, both strength and stiffness, you know, because we have it in such controlled environment. I think that's an important thing to note of you have to kind of know what the environment, what the threat assessment is, right? Because I do think we do successfully for 60 years design to pristine where appropriate. And that's an important distinction.
And you use proof testing too, right, Dan? That's been a pretty integral part of the Goddard approach too, right?
What's that?
Proof testing has been an integral part of that approach.
Proto-flight testing, yes, absolutely, at the
Yeah,
full scale
yep.
level. Yep. So let's see. I see one question here from Jacob. Hi, Jeremy. Given the sensitivity of composites to damage, could you comment further on any opportunities you see for future improvement in damage-tolerant demonstration protection?
Absolutely. I think there's plenty other folks that would like to chime in on that. To date, I didn't get a chance to talk about the spacesuit much, but one of our biggest opportunities there for the moon suit is got to be really light. We gotta design to fall down in that spacesuit, right? Bang into things. And to date, when we've really pushed damage tolerance from an aggressive standpoint, our current matrix systems just don't work with carbon. And it turns out that, you know, there's some things you can do like three-dimensional woven structures, and we've had big improvement matrix materials instead of epoxies or Um, and we've made big improvements on damage tolerance by using three-dimensionally woven structures. Dan Polis is a champion of the pie joint technology, and it's been very, very damage tolerant in comparison. But if you're talking about real significant impact energies, our spacesuit needs to be designed to 172 foot-pounds of energy, and there's a whole story behind that. It's huge. It's bigger than what the airplanes are designing to.
Thank you. Next question. Seems very focused on one-time use space exploration structures. Is NASA doing much design, material process development to support reusable commercial space?
Oh, absolutely. Yeah, reusability is baked into our CST 100 Starliner. It was designed for that intentionally, and as you probably are aware, the SpaceX Dragon, we're into heavy reuse with that vehicle as well. So absolutely.
All right.
Big story even isn't that significant, really. It's more thermal.
In the chat, do you see any movement to more thermoplastics versus thermosets?
So to date, you'll see that more in sporting goods. And I know Spirit is working on it. There's a number of others that are working thermoplastics. I absolutely see opportunity in thermoplastics, and the general toughness improvement is very apparent. We don't have any parts that I'm working on
Yeah, NASA does have a big thrust, I think, in that area, and it's mainly on in space manufacturing using thermoplastics. Let's see. How about last question? What would be ideal mass reduction for making human spaceflight cheaper and accessible to all of us? Tough one.
Yeah, tough one. Well, no, I shouldn't say that either. But really, our biggest. So I've spent my whole life working in structures and materials, right? And I'm trying to think of the number of times where the structure was the thing that failed, right? Reliable, cheaper access to space is real technology. That's the riskiest part of it. It's the most expensive. Saying there are places for improvement, right, on structure. I don't know, Dan, you have my. That's a great question.
Yeah, I mean, I guess I think about dollars per pound. Anywhere from $10,000 per pound to launch to 50,000, depending on what your vehicle is on your mission. So you can imagine how much you save by a full thrust structure, for instance, in that regard. So I think we're out of time. I want to do a public service announcement at the end. First, Jeremy, thank you so much for participating. It was really great, great to catch up. Thanks everybody in the audience. Even with audio issues, really looked like everybody hung in there. So that really goes a long way to say great engagement with the audience. And then the last thing I'll say before the holidays, as you're looking to, excuse me, as you're looking to participate in 2024, if you're interested in these topics, please join on SAMPy 365, the Space Applications Technical Committee, or reach out to Chris, myself, or Jaden. We could really use contributors. I think that the webinar series has gotten people involved, but we really want to find topics that we have common interest that we can make progress on, and we'll be talking more about that in 2024. So with that, thanks everybody. Thanks, Jeremy.
You bet. Happy holidays, everybody.